Hi, welcome back. This is Professor Ridge, and today's lesson on section 3.5, solving equations and inequalities with absolute value. Okay, so equations with absolute value. For a is greater than 0, so a is positive, and an algebraic expression x, so it could be something simple like just x, or something more complicated, 5x plus 7, or even more complicated than that. Okay, so the absolute value of this algebraic expression x is equal to a is equivalent to x equals negative a or x equals a. Okay, so we can have something as simple as just x itself. So absolute value x. Now remember, to be a solution to an equation means any replacement value of the variable that makes a statement true. So there's two cases. X, the number inside the absolute value, x could be either negative 5, because the absolute value of negative 5 is 5, or x could be equal to positive 5. And then you solve the resulting equation, right? So let's try another example. Solve, say, 3x plus 2, absolute value of 3x plus 2, minus 1 equals, say, 12. Okay, so the first step is you want to isolate the absolute value. Okay, so we got absolute value 3x plus 2. We're going to add 1 to both sides, equals 13. Now once you do that, apply the rule above. The other way I think of it is actually split it in two cases. The number inside this absolute value could be either negative 13, or the number inside the absolute value, the expression inside the absolute value, could be equal to positive 13. So you split it into two cases. Alright, and then you solve the resulting equations. Okay, so it's just two separate equations you solve separately. So divide by 3, so x equals negative 5, or subtract 2, divide by 3, x equals 11 thirds. So you get negative 5 or 11 thirds, the two individual points. Right, so if we put it in solution set, negative 5, comma, 11, 3. If I graph it, it's just the two dots. Okay, so now let's look at inequalities with absolute value. Okay, so let's look at inequalities with absolute value. So again, if a is positive, a is greater than 0, and you have an algebraic expression x, the absolute value of x is less than a is equivalent to x is between negative a and a. So it's negative a is less than your algebraic expression, x is less than a. And then if it's greater than, absolute value of x is greater than a is equivalent to your expression is going to be greater than, or no, it's going to be less than negative a or greater than a. Okay, and then if we have the less than or equal to or greater than or equal, same thing, same statements, but just put the equal to sign under the inequality. Okay, so similar statements for both of those. All right, let's try a couple of those examples. Okay, so if we solve absolute value of x plus 9 is greater than 12, so greater than statement, you got to remember that it's an OR statement. It's x plus 9 is less than negative 12. So I always remember the one where I changed the sign, I changed the inequality also. And then x plus 9 is greater than 12. So the one that I leave alone, I just drop the bars, leave everything alone. Okay, so subtract 9, when I mean drop the absolute value bars. So x is less than negative 21, or x is greater than 3. So again, if we looked at a number line, negative 21, x is greater or is less than negative 21, and x is greater than 3. So if I wrote my solution set, I can have my solution as a graph or write it in interval notation, negative infinity to negative 21, union 3 to infinity. Let's try another example. So let's solve absolute value of 5 minus 2x plus 3 is greater than 10. So my first step is I'm going to subtract 3. You got to isolate the absolute value to apply the principle. Okay, greater than statement. So again, it's an OR statement, so I'm going to go 5 minus 2x is less than negative 7, or 5 minus 2x is greater than 7. So let's see, now I'm going to solve these separately. So negative 2x is less than negative 12. When you divide both sides by a negative, don't forget you got to flip the inequality again. So that's x is greater than 6. Or subtract 5. It's greater than 2. Divide by negative 2. X is greater than negative 1. Oops. Got to flip the inequality. X is less than 1. Negative 1. So x is greater than 6. And then x is less than negative 1. So again, if I do interval notation, negative infinity to negative 1, union 6 to infinity. Now let's try one that's less than. So if I have 3x minus 2, absolute value of that is less than 15. Less than statement, you got to remember, is a compound inequality that's in between. I'm sorry, so it's in between negative 15 and 15. So you write the number that's inside the square root in the middle, and then you sandwich it between two less than symbols, and then the negative 15 goes on the left, positive 15 on the right, and then we're going to solve this. So add 2 to all three pieces. Negative 13 is less than 3x, which is less than 17. Divide by 3, so we got x is between negative 13 thirds and 17 thirds. So that would be, okay, I'm not going to do the graph. The interval notation would be between negative 13 thirds and 17 thirds. Let's try another one of those, but with an equal to sign. So if I did 2x plus 5 is less than or equal to, say 27. So again, it's a less than statement. So I put the 2x plus 5 in the middle of two less thans, and go negative 27, positive 27. So negative 27 is less than or equal to 2x plus 5, which is less than or equal to 27. So we subtract 5 from all three pieces. We want to get x by itself in the middle. And then divide all three pieces by 2 to get x by itself. So we get negative 16 is less than or equal to x, which is less than or equal to 11. And again, I'm going to use brackets now because the equal to, we're including the endpoints. So it's all the numbers between negative 16 and 11, including the two endpoints. So it could be negative 16 and it could be 11, or anything in between. Alright, so that completes the exercises for 3.5. Go to My Math Lab, complete your homework there, and I'll see you next time.